Let's look at some extra examples with counting principle, permutations, and combinations. So again, the big thing to note in every problem before you decide which way to attack it is what's your setup? What kind of combination or permutation or order is going to be important? So again, permutations order is important. Combinations, it's just the size of the group. And you can use counting principle if you have multiple potential choices that you're trying to stack up on each other. So example 1, we have 3 students, Andy, Beth, and Kara, have to arrange their desks in a row in a classroom. Your job is to figure out how many different arrangements they can make. So is order important? Absolutely. So that means this is a permutation. So we're going to do NPR. And again, we're looking at, those 3 people, arranging them all the different possible orders. We're going to do 3 people, which means if they're all seated, they have to have 3 people in the row. So 3P3, otherwise known as 3 times 2 times 1, aka 6. So let's make sure that this math makes sense. So we could have one order, A, B, C. Okay, well, let's flip the next 2. So CB. And then what if Beth came first? So then we'd have Beth, and then our combination could be A and C, or C and A. And what if Kara came first? So C, leftovers A and B, and then flip-flop them. Did that work? Yep, 6 different combinations, and we have all the possibilities listed out. Okay, number 2, Dana is added to the group of students in number 1 above. So how would that change things? Well, now, how many students have we got versus how many have to be in each row? Well, all 4. So we're going to do 4P4, otherwise known as 4 times 3 times 2 times 1, which multiplied out comes out to 24 different ways for that arrangement. Alrighty, number 3, Mr. Smith's class wants to elect president, vice president, and treasurer. So is that order is important or it's not? Specific offices, absolutely, order is important. So even though he listed out every single person's name, do we really need to map those out? We just need to use a permutation. So we have how many students? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 students. So we have 19 to choose from. And we need to make a group of president, vice president, treasurer. So we need to pick 3. So 19, pick 3. Again, plug that in your calculator. Should come out to 5814. All right, problem number 4. Mr. Smith's class wants to create a dress code committee composed of 3 students. Using the student names in number 3 above, how many different committees are possible? So again, if we use all possible 19 students, well, does order matter if it's just a committee? No, it's just a group of students working together. So now we're going to do 19, choose 3. So again, change up how you plug it in on your calculator. That's going to come out to 969 different committees that you could create. So how are they different? Well, again, one of them order matters and the other doesn't. So the order is how it changes it up. Alrighty, number 6. Bill has 3 hats, 5 shirts, and 10 pairs of pants, and 6 pairs of shoes. If an outfit consists of a hat, a shirt, a pair of pants, and a pair of shoes, so he has to choose one from each of those groups, how many different outfits does Bill have? So because he has the 4 different categories that he has to choose from, and multiple choices in each one, this is a counting principle problem. So he has to pick a hat. How many choices? He's got 3. He's got to pick a shirt. 5 choices. He has to pick a pair of pants. 10 choices. And he has to pick a pair of shoes. So that's 6 choices. Multiply them together. That's how many different outfits. So we could make 900 outfits on this one. Alrighty, pizza. And I'm recording this close to dinner, so I might have to take my dinner break after this video. Okay, Joe's Pizza has the following optional toppings: pepperoni, sausage, peppers, and onions. So there's 4 different choices. All pizzas automatically come with cheese. So how many different combinations of toppings are possible? Show all of them or describe them in such a way that you show you have accounted for all the possibilities. So here's the deal again. Doesn't matter what order you put those toppings on the pizza. Not really. So it's just about which ones you're choosing to use. So you could have a 1-topping pizza, 2 toppings, 3 toppings, or 4 toppings. So you have 1 topping. I'm just going to abbreviate as top. So that means you have 4. You're choosing 1 out of those choices. Again, there's only 4 choices, and you could plug that in the calculator absolutely if you wanted to. So we're going to have to use that as part of it. So what if we had 2 toppings? Well, out of 4, if we're choosing 2, how many combinations? You could actually do 6 different combinations of 2 toppings. And again, if you plug in 4C2 in calculator of choice, should get out an answer of 6. Okay, 3 toppings, 4 choices. We're trying to choose a group of 3. There's actually only 4 ways to do it. And then if we're choosing 4 toppings, but we only have 4 to choose from, how many different combinations could we have? Well, just one that has all 4 toppings. And so what we're going to do then, if the question was asking, how many different possible combinations can we have depending on how many toppings, we're going to take all these final answers and add them all up together. So 4 plus 6 plus 4 plus 1. That means total, if all you have available is 4 toppings, you have 15 possible different combinations that you could make. Alrighty, number 8. Simplify the factorial expressions. So for this, it's all about just plugging in the calculator. And again, if you're using Desmos, all you have to do is type it in exactly the way it looks. So actually, let me pop over to Desmos real quick. So let me change my screen share and go over to Desmos. So again, all we're going to do is, let me delete out what I had from my previous problems. We're just going to type it in exactly the way it looks. So we need to do 5 factorial. Now, again, if you're on a touchscreen like me and you don't have a computer, that means you're going to have to go to the ABC, and right down below, that's where that exclamation point is. And then back over my number pad, and I'm going to divide, and it automatically puts my fraction bar in there. So then I need 3 exclamation point. So our final answer on that one is 20. And that's all we have to do on these, is make sure that we're typing them in the order that we see them in. So when you type in the 5 factorial divided by 3 factorial, again, you get out 20 as your answer. Let me switch back over to our main screen. There we go. So that one should come out as 20. Again, B, if you type it in exactly the same way, should come out as 210. Be careful when you have multiple values. So if we're doing 8 factorial divided by 5 factorial times 3 factorial, just make sure that you're careful of where you're plugging things in your fraction. As long as you're careful with that, then you're good to go. If you're doing this on a TI calculator, I would go ahead and put the entire denominator, and actually every single one of those, I would always put the denominator in a set of parentheses, because again, your TI calculator is a little bit more sensitive with order of operations, especially if you have an older one and you can't type it in so it has the, fraction with numerator over denominator. So C, when you plug that in, you should get 56. D should be 252. And I want to take a closer look at E. So 900 factorial times 898 factorial. So if we think about the definition of what factorial means, it means we're multiplying every integer starting with that one and then going down by 1. So the numerator is really 900 times 899 times 898 times 897 and going down from there. 898 factorial starts at 898 times 897 and it goes down from there. Wait a second, I have some repeated values. So if I continue my pattern in the numerator, 898, 897, all the way down to 1, I'm going to have exactly the same values in the denominator. So officially, if I was doing this by hand, I could completely cancel that out. And then all I would have left is whatever 900 times 899 is, which gives me a very large number, actually. It gives me 809100. But again, exactly the same value that should come in when you plug it in the calculator, as long as you're careful with typing it in. Okay, few more permutation and combination patterns. Okay, number 9, manager of a baseball team has named the 9 starters for the game, but he needs to make the starting lineup, or the batting order rather. So how many batting orders are possible? So is order important? Absolutely, because you need to know, who's going to start off the game. So order is important, which means we're going to use a permutation. So we have 9 possible starters, and all 9 of them need to go in that batting order for that inning. Alrighty, so 9 permutation 9. In other words, 9 times 8 times 7 all the way down. Same thing as 9 factorial, in fact, if we want to use it that way. Or you could literally just plug 9p9 into your calculator. And you'll be surprised, you actually get a large number of combinations. There are 362,880 ways to arrange those 9 people in order. Again, permutations are definitely going to have the higher valued answers. Combinations, not so much, because the order is not important rather. Okay, number 10, 33 cars in a car race, first, second, and third place. So is order important? Absolutely, we need a permutation. So 33 cards to choose from. First, second, and third place, so the first 3 positions only. So 33, pick 3. So again, plug in that in the calculator, or this is 33 times 32 times 31, because only 3 places to choose. Either way, you should get out 32,736 possible combinations, picks of order for those first, second, and third place. Alrighty, whoops, sorry about that. So license plates in a certain country contain a permutation of exactly 5 letters. Definitely not the United States. We have 7 possible letters or 7 possible digits that could be letters or numbers. So obviously a location that doesn't have as many cars as in the United States. If if no letter can be repeated, how many different letter permutations are possible? So right off the bat, it's telling us it's a permutation. The order is important because, we could have some of the or different letters in a different order to make a new license plate. Okay, they said we had 5 letters that we had to pick, but how many letters are there? Or in the alphabet, we have 26 letters. So that means we need to pick 5 out of 26. So 26, pick 5. Alrighty, so multiply that out. We have 7,893,600 possible letter permutations. Not nearly enough for the United States. That is why we bumped it up to 7, and it's now letters and numbers. So we could pick a whole lot of different options in there. Alrighty. The manager of a baseball team has to select 9 starters from a game. Wait a second, is this the same problem? No. She has 11 players to choose from now. Okay, so different problem than before, but how many combinations of 9 players can she choose? So is she worried about the order of the people she's picking? No, not at this point. So combinations, again, order doesn't matter. So that means we're going to use the combination, or the C. We have 11 to choose from, and we've got to choose a group of 9. And then probably later then she's going to put them in starting order. Okay, so 11, C9. Again, plug in your calculator of choice. You should get 55. Again, much lower than if this was a permutation problem. Okay, number 13. A committee of 5 students is selected from a class of 20. Is order important? Nope. Combination problem again. So 20 to choose from, committee of 5. So again, plug in your calculator. We're going to have 15,504 possible committees. Alrighty, last practice problem. The special combo pizza at Ciro's Pizza includes any 5 toppings from the list of 16. How many different combo pizzas are possible? So again, is order important? They're using a combination of toppings. They could technically be put in any order on the pizza. So, combination. Any 5 toppings from the list of 16. So, 16, choosing 5. All right, so that's not necessarily taking into account all the extras. So we are kind of generalizing this problem a little bit. However, 16, choose 5. Calculate that out there, 4,368 possible combination pizzas that you could make with 5 toppings. So again, you could extend a couple of these problems, and if you're interested or curious, please do, investigate the other options or ask me about any problems that you want to look a little further into. If not, get going on your graded practice. Have a great day.